Robotics really is this overlapping three parts. There is the hardware, the sensing and control piece of it, and then there's this last part of the software to make it basically react to the environment, to sense what is going on, take the inputs from what I would say is the electronics, react to that and do something appropriate.
Our students get a very good training in computational field, like computer engineering. They learn mechanics, kinematics, dynamics. They learn very important control theory.
What we teach them is this combination of hardware, electronics, software, systems engineering. How do I architect a big system with lots of complicated parts and make it work?
Robotics requires expertise in modeling the systems, so mathematical modeling and simulation. Also how to program the algorithms that will control the physical moving parts of a robotic system.
Here at the Jack Baskin School of Engineering, we get this in at an undergraduate level. We get students working on real problems. We supplement that with the theory that they need to be able to tackle those problems, and we integrate it all together in kind of one place at one time.
The other thing which is different than any other university I've been in, it's a loose boundary between departments. I have a variety of collaborators which are from other parts of the school. It turns out that my students are designing snake robots, which are all flexible. They can go in small spaces and they can be used for rescue. My colleagues in biology happen to have the real snakes, and we learn so much from each other and so on.
Unofficial name of my lab was given by students a long time ago. It's a desktop robotics because, as you can see, all the robots that I show you can fit on a desk. It's not always the case that you can work on a theory and then be able to demonstrate the theory on a small scale without further investment in building something large. For NASA, for example, we use this EPAC and program it to move as a Boeing 747 in a scaled-down robot experiments to collect data to understand how the aircraft move over the airport.
Traditional robots are interesting and they're really well suited for certain fields, but the emerging field of soft robots brings us a whole new set of parameters. These soft systems lend themselves to interaction with human beings because they're inexpensive and soft, and the likelihood is very low of them hurting a human being.
The ultimate goal of our research is to create a robot which is so soft and so wearable that you actually are not going to feel much and you can go about and do your daily activities. Our second goal is to create cooperative robots which can talk to each other and fly together. So our main collaborators here are the US Geological Survey and NASA Ames. They want to understand how different phenomena in atmosphere, volcanoes, earthquakes, tectonic plates are working.
One of the things I'm really excited about is this drone traffic management systems, and this is really futuristic vision. The long-term vision is having this completely dedicated traffic management system, no human in the loop.
Many of the physical concepts are quite well understood in many cases. The question now is how do we program them? How do we, through software, through algorithms, make them do the things we want them to do?
Control theory is the science of decision-making and taking actions.
The science that provides mathematical guarantees to get systems do what you would like them to do.
To make it basically react to the environment and do something appropriate.
Robotics is a very interdisciplinary field. The curriculum gives you an introduction to electrical engineering. You get so much background in computer science and computer engineering. You really are just a roboticist by the end.
I'm really interested in kind of building robots to help people. So my snake robot, I wanted to kind of help like search and rescue missions.
I want to be able to make something and directly influence someone's life. And so that's the most inspirational thing that I can see from robotics.
To me, it's most interesting to see that I can work on something that no one's ever done before.
Robotics, self-driving cars, self-flying drones. We really have a lot of opportunities at UC Santa Cruz, and that is a very exciting future.